Hello everybody, welcome to our first video of calculus. Woohoo! Alright, we're beginning at chapter 1.1 and this is our preview of calculus. Our following objectives are we're going to understand how calculus compares with pre-calculus. We're going to introduce the two problems that are very basic to calculus, the problem of the tangent line and the problem of area, specifically area under the curve. Alright, so let's just jump right in here. Now, our discussion today is going to focus around two concepts. These two concepts are going to be rate of change and area. And we're going to talk about how our approach to them is going to differ between pre-calculus, what we used to do, versus the way calculus teaches us to handle this problem. So, we're going to begin with rate of change. Rate of change. And in pre-calculus, we dealt with rate of change in two ways. It was our slope. Let me try and fix this focus here a little bit. There we go. We knew it as, there we go, is that better? Maybe a little bit. Let's try this. There we go. We knew it as slope, so you can write that. And also, we only ever dealt with linear data. So, for example, in pre-calculus, we had the following sorts of graphs. We had a coordinate plane, and we would have a set of linear data that would make a line, right? So here's our line, say, of linear data. And we would define rate of change as, hang on, I'm still trying to fix this focus here. I think that might help a little bit. Maybe if I move back. Give me 1 second, everybody. Let's see if this helps. There we go. That's a little bit more clear. Okay. So we would have any 2 points, and the first we would call our x and our f of x value. We would have an x value, and then we would put that into our function and get our y value, or f of x value. And then our second point we could call x plus the change in x, because you'll notice from this point to this point there was a change in our x values. We added some x, so we call this the change in x from this point to this point. So we added that change in x to our original x, and then we found our function at this x plus change in x. Okay, so this basically just describes any two coordinates on some linear data on a line. And in pre-calculus, we would define the rate of change between these 2 points with that slope formula. And remember, that looks like the change in y over the change in x. And specifically, we would do y2 minus y1 over x2 minus x1. So let's label what these are. This would be our y2, our x2, our y1, and our x1. And so if we plug those into our slope formula that we know so well, we would have f of x plus change in x minus f of x, y2 minus y1. And then on the bottom we would have x2, x plus change in x, minus x1, or just x. Now, you guys are pros at algebra by now. You can see in the denominator here that what we've got going on is something that can cancel. We have a positive x here and a minus x here, so we get to cross those out, and our new simplified slope formula looks like this. F of x plus the change in x minus f of x all over the change in x. And this would tell us our average rate of change. We can write that below. Average rate of change, or simply slope. That's what we know it best as. Now, that's how we approached it in pre-calculus. In calculus, we have a different approach. In calculus, what we need to know is with non-linear data, we're interested in the instantaneous, there we go, rate of change. And we're going to draw a quick graph of what that looks like. So if we had a coordinate plane, say, and we had a piece of non-linear data, that would just be curved data. So it might look something like this. Here is our graph of non-linear data. And remember what we talked about in class. Whenever we have a curved set of data, we no longer have just one slope. If we take a look at this, the point here has a different slope than the point here. The point on the line here has a much different slope than the point on the line here. We have different slopes at every point on this line. So in calculus, we are no longer interested in this average rate of change. That isn't useful to us anymore with curved data. What is useful to us is finding the rate of change at any one of those points on this line. And we can do that the following way. So say we had a point P, mark a little point P on your graph there, and we're going to write out some thoughts here. So our first thought is that we want to know the instantaneous rate of change, and we'll say at point P. That's what we want to know. And we know we can do that. We can find the instantaneous rate of change if we can find the instantaneous rate of change, or the slope of the point P, if we find the slope of the line through point P. And we call that line through point P, you can just underline that, line through point P, that's going to be called our tangent line. And here's what I mean by that. So draw a line with me that goes right through P and has the same slope at that point. So our tangent line at P might look something like this. It's a straight line because all linear equations look just like straight lines. And you can see that this line goes through point P and it has the exact same rate of change as this point. And so we can find the slope of that line, and then we'll have the slope of the point. However, it's important to realize something. It's important to realize that we can't, I'm going to underline that, find the slope at only one point. And here's why. Let's illustrate why. Let's take that original rate of change function, our slope function, f of x plus the change in x, minus f of x all over the change in x. Okay. Finding the slope at one point means that there is no change in x anymore. If we're comparing only one point, we didn't do this anymore. We didn't move our x at all, right? If we just stayed here the whole time, the change in x wouldn't even happen. So that means in our equation here, in our expression for slope, for rate of change, we would have to fill in 0 for change in x. And you guys know by now that if we did that, if we filled in 0 on the bottom for change in x, and we filled in 0 on the top for change in x, we would just get on top f of x minus f of x, which would be 0, and on the bottom we'd have 0, and we know we can't have 0 at the bottom of a fraction. This would be a mess. It would never work. So we want that slope at one point, but it turns out we can't use our traditional way of getting there because our traditional equation for slope has no way to tell us only one point. So here's what we do in calculus. In calculus, just keep on writing those thoughts out for me. I'll just keep on tracking our thought pattern here. What we can do is find slopes of lines that are very, very close to our point. And we call these lines secant lines. So let's illustrate what those look like real quick. So say that we had our same graph. We're still going to have the same point P. Let me review what that looked like real quick. I forgot what I drew. Okay. So if we had the same graph, and we still had our point P, and our tangent line was what we had before, right, in red. Let's keep on drawing that, make sure we stay consistent here. That one was our tangent line because it has the exact same slope as our point, and we can even label that, say, tan for tangent. Our secant lines are going to do this. They might start out here at a point that's pretty close and make it through our point P. And then, as you'll see, these points are just going to get closer to point P. Check it out. We're moving a little bit closer to point P. We're going to make another line. And these lines are going to get stacked on top of each other. They might look a little bit messy, but it's just important that we understand the process as we create them. And check it out. We can still add another point in here. Let's add another point even closer to P. Wow, check out this little tiny line. Isn't that slope very, very close to the tangent line slope? See what's happening here, guys? Oh my goodness, that one was almost exactly our tangent line. So you see the point I'm illustrating. As we move our secant lines closer and closer and closer to our point P, we actually approach almost exactly the same slope as that original tangent line. And that's the whole point. So now that we know what secant lines do and now that we know what our focus is going to be, we're going to do an example of this. So say we had the example, consider the function f of x equals x cubed. Use secant lines to approximate the instantaneous rate of change when x equals 2. All right, so we're going to do exactly what we talked about with creating those secant lines. And we're going to make those secant points, the points for our lines, very, very, very close to 2 so that we can figure out, we can look at all of the slopes at points that get really, really close to 2, and we can see what they average out to be, and then we can essentially just consider that our slope at 2. So here's what I mean. If we set up a table, and again, we want to pick points that are very, very close to 2. So let's pick points like 2.01, 2.001, 2.0001. Okay, let's do one more. 2.00001. And we plug these in for y. We're going to find out some pretty cool stuff. All right. If we plug in 2.01 to f of x cubed, if we cube 2.01, we get 8.121. And then what we're going to do is we're going to use these 2 points as our values for that rate of change formula. So remember our rate of change formula, recall that we have f of x plus the change in x minus f of x all over the change in x. Well, for this first value here, 2.01 and 8.121, f of x plus the change in x, that's our y right here. That's our 2 plus this 0.01. We plugged that in, and this was our output. So the output we're going to fill in for the first value is 8.121, and then we're going to subtract f of x, f of our x at 2. And we all know 2, if we plug this into our formula, 2 cubed would be 8. So our f of x value is going to be 8. And then the change in x, the change from the 2 to the 2.01 is just 0.01. And if we simplify this out, we get 12.1. Okay, let's try our next point. If we cube 2.001, then we get the value 8.012. All right, let's keep plugging into our rate of change formula. Our f of x plus change in x in this case is going to be 8.012. Our f of x, our f at 2, is still 8. And our change in x this time got a little bit smaller. Now it's 0.001. And when we subtract and then divide, we get 12. All right, looking pretty good. Let's try this next point. If we take 2.0001 and we cube it, we plug it into our f of x cubed, we get the value 8.0012. And when we plug that into our formula for our f of x plus the change in x, minus 8, all over our change in, oh, pardon me, missing a 0, our change in x, which is now 0.0001, we get 12 again. Interesting. Okay. And the last one we're going to plug in, 2.00001. If we cube that number, then we get the value 8.00012. And same thing, we're going to plug this into our rate of change formula, 8.00012 minus 8, all over our change in x, which is now 0.00001. And we get, again, 12. All right, let's talk about what this means. On our graph, our f of x cubed, we can't plug in the 1 point like we talked about, but what we can do is look at all the other points that are very, 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 very close to that point. 2.01 is close. These are all very, very close to 2. And we can find the slopes between the point we want to know and the points that are very close to it. And we found that all of those slopes got very, very, very close to 12. And so what we just did, you guys, is called the limit. We just found the limit of the slopes of the secant lines. And what we can also think of this as is, I'm going to write AKA, also known as the value that the slopes approach. And we can see the value that are all those slopes that get really, really close to our point, they approach 12. So what we can do with calculus is, since we got so close to 2 and our slope was 12, we can say that the limit of the graph as we approach 2 is 12. And we can even write that down here in words. We can say the slope of the tangent line to the graph f of x equals x cubed at x equals 2 is approximately 12. Okay, that's what we can do with calculus when it comes to curved data. The last thing we're going to talk about today is going to be area under a curve. And again, we have two different approaches to this. In pre-calculus, we had a very straightforward approach. Again, in pre-calculus, we deal with that linear data. And so say here's our line. And then say we would have units. This would be the point 4, 0, and say we have the point 0, 4 up here. We could find the area under this curve in a pretty straightforward way in pre-calculus. What we could do is use our knowledge of the area for triangles. Base times height times 1/2. And we could say, well, 4 times 4 times 1/2 would just be 8, and we would be done. However, just like before, what calculus lets us deal with is that non-linear data. So we would have a graph in calculus with something closer to this. Maybe we would have a curve that goes straight up, and we're interested in knowing the area I don't know, we can call this point, let's call this point, I'm not sure, 3, 0. So we want to know the area bounded by the graph. We'll just call this graph f of x. F of x, we'll call this one x equals 3, and then on the x-axis here, y equals 0. So you can see it's bounded here on the bottom, here where x equals 3, and then by our graph f of x. So we're just interested in this section right here. And what calculus lets us do, you can see that there is no formula for finding a curve, right? We can't just call this a triangle, call it good enough, and use this formula. We can't do that. We need to be more accurate. And in calculus, the way that we do that is we split this up into rectangles. So let's get some rectangles going here. And we just make sure that they touch our data. And then we would take the area of each rectangle, and that is how we would approximate the area under the graph, under the curve. However, what I want you guys to think about is, what could we do to this amount of rectangles? Right now, just by drawing 3, it doesn't look like I'm going to be that accurate, right? All of this area that I'm about to color in red would be extra, and that would be inaccurate, right? Well, here's what we can do. In calculus, we can find the area under the curve if we keep on making more rectangles. So let's consider this graph. Same thing, we still have that curve going on, and we'll still have everything bounded at 3, 0. But check it out. What if I doubled the amount of rectangles? What if I did 1 here, 1 here, 1 here, here. Oh my gosh, check it out. Now, look at all of our little pieces in red, right? All of our little mistakes that we know are inaccurate. It looks like we're having less of that red space. And that's the fundamental problem with area for calculus. It's important to realize that we can't ever find like the exact area under a curve. There's no real way to do that. So in calculus, what we do is we take all these rectangles and we just keep making more and more and more. And we take that limit, just like we took the limit as those secant values got closer and closer to 2, we take the limit as the number of rectangles gets closer and closer to infinity, right? Because if we kept on making rectangles, we would have fewer and fewer error up here. And then we call that the approximation for the whole area under the graph. Okay. Though that is essentially all I have for you today. We'll talk more in class. We'll graph more in class. I have something interesting to show you on your calculators. And that is it for this video. So thanks for watching. We'll see you in class tomorrow.